Let's do this thing. Hey everybody, hope you're doing well today. Today we're going to be covering setting up threads. We're specifically controlling them and stopping and starting them and the different ways to create them. There are kind of two distinct ways to do it in Zephyr, one using a macro and one just using it kind of calling runtime functions. So we'll dive into those both today. And today was another community-inspired question from a previous video on stack allocation. So I put that link in the description box below. You can check it out when you're done watching this, of course. And if you haven't already, please do subscribe, hit that like button, and let's get to 1,000 likes. I think we're almost there, or 1,000 subscribers. That'd be awesome. I really appreciate you all being here, and maybe I'll do something special for that 1,000. We'll see what happens. But let's dive in. So this is the question: is it possible to dynamically create a thread and define its stack? So let's talk about it. So in general, Zephyr is an RTOS which allows you to run many threads, as many as your hardware supports, i.e. you are limited by your memory allocation. So as long as you have allocated stack space, you should be able to switch through an unlimited amount of threads. But like we said, it's limited by memory. Execution is consecutive in Zephyr, so one at a time because you are sharing a CPU. In general, that's not a big deal, but if you have some real-time running tasks, there are some dual-core ARM processors out there now that you can kind of run tasks on different processors, which is helpful. But in the most part, we're talking about a single core, so we're just running things one at a time. And there are some ways to juggle that, especially with Zephyr threads. Maybe you have different priorities over different types of processes that you're running. Application code, let's say you have some time-dependent things going on. You can set, like if you're trying to service a UART receive buffer or something like that, that's a higher priority task than maybe something that's going on in your application code, which can kind of happen anytime. So you can set those priorities as you need to. So, and yeah, so priorities. So steps for creating a thread: you're going to set up your stack area. This is probably one of the more important things that I just kind of mentioned. It's just setting up how much space you think your stack or your thread is going to be using on the stack. Generally, you kind of tune it to what you think is best, and you can always use something like a thread analyzer, things like that during runtime to see how much you're actually using. So you set up your thread context. You create your thread using the create function, and alternatively, you can use the macro kind of I mentioned earlier. It's a k underscore thread underscore define, and that will do kind of everything above. So, but we'll dive into both, and you'll see both here today. So, the important thing here is you can't create a thread without creating a stack area. So, if you're thinking like, oh, I can just like create a thread during runtime and allocate space and things like that, and doesn't quite work that way. You do have to allocate some stack space, so when everything compiles together, that's allocated to you at compile time. So whether or not you use it in your code, maybe you don't even start your thread in the code for 99% of the life of your application, it's still allocated to that particular thread. So keep that in mind. Just remember that. That's probably the biggest thing for allocating any type of memory or starting a thread from in runtime. So here's a quick example. I kind of pulled it out of one of the samples I have on the NF9160 Feather repository. This was a UART processing thread, so I just set it up for processing incoming data. It's called UART thread. That function is going to be called when the thread starts. Indicated. I'll actually run through here because I'll point out some important things here. So we're going to go through using the macro first. So this macro basically does a bunch of stuff at the beginning, and also sets your thread to be run as soon as possible or within a delay period. So I'll show that in a second. But we can use this thread ID to actually start and stop later on in the code, and I'll get to those functions shortly. So that's handy to know. The next thing is what happened there? There's one important thing that I left out of the function there. You can set the size, the stack size, and that resized for some reason, but the stack size is the approximate size that you think is going to work for your application for that particular thread. So that's important. And the thing that I missed, I didn't include in that first slide, was that the UART thread, generally, if you want it to run perpetually, then you need to put in some type of infinite loop or something like that to keep that thread alive. Because if you just let that thread, if you remove that while loop or whatever, and we'll get to termination in a second, but if you get rid of that while loop, it's just going to fall through and then it's going to terminate your thread. So something important to know. These are parameters that you can pass. Actually, I think that the thread function actually allows you to pass 3 parameters for whatever reason here. The compiler let me compile with only 1 parameter. So that's something that you can do at any point in time. For the most part, I generally don't, because you can also still access the static variables and things like that as needed. But if you're using something that you might be concerned about, or maybe it's something that is completely separate from this particular piece of code, or like somewhere else in your application, you can always pass things to it. By default, in many cases, you can just use the system lowest application thread priority. But like I mentioned before, if you have something that's processing something and it's very needs to be timely, then you'll have to adjust your application priority. And then depending on how your Zephyr configuration and your processor and everything like that is set up, your application priorities will range. Typically, it's like negative up to positive. And these are either cooperative or preemptive thread types. And the preemptive, I think, are the highest priority threads, and I think it's the negative all the way down to the negative. So depending on your application, I think the lowest application thread priority is the lowest cooperative, I believe. But please correct me in the comments if I'm wrong. Priority, there are some options you can set, and generally I don't set them and didn't set them for this sample as well. And then this is the start delay, which in milliseconds, so you can kind of delay the start of a thread at the beginning of your application if you want. I don't really see a point in this. Generally, you'd want to start a thread once something is ready. But there's also some ways, like if we go back to I did do a video on thread or semaphores and things like that. You can go back there and see that I have used kind of semaphores to prevent a thread from continuing execution. So that's one way you can do it, or you can create a thread and some time later in your application, and then that'll continue execution. So there's the idea here. So it's great if you want it to start when your application starts. So you don't really care. Maybe you have it going on. Maybe you have some thread control outside of kind of the thread or the thread API. And you can also delay it, as like I said. But what if we don't want it to execute immediately? So beyond setting a delay, we can actually create the thread manually. And it's what that macro does kind of underneath the hood. So let's check that out. So it's the same sample here. Creating this UART thread with the infinite loop there that's doing something inside, processing message queues, processing FIFO data, things like that. The only differences here is that we're actually defining the stack area. So we're creating that stack area, which is also what that macro does underneath the hood. We're also creating kind of this like K thread. It's like a context. So it's just data to track the thread as it's being executed or used. It's generally used by the kernel and the process control. You can see that there. This is the most important part right here. So somewhere later in your code, maybe in your main function, maybe somewhere else. If you want to start using or you want to create and spawn this thread, this function will actually create and spawn the thread. So we're taking that thread data, that stack area data, and we're, or actually the context and then the stack area. There's those first two parameters, and then we're getting the stack, the size of that stack, and then we're referencing that same UART thread. So as you can see, besides those first three parameters, it's very similar to the kthread define macro. All the other entries are the same. So you have the thread function, the parameters if you want to put them there, priority, options, and the timeout. So in this case, there's just no wait, which is also equal to 0, I believe. Once it's started, so whether or not you create the thread with the macro or with this create function, you can actually start, stop, abort. There's a bunch of different API calls that you can use to control it as during execution, which is handy. These are probably the more important ones, is the suspend and resume. These are most likely the ones you're going to be using in your code if you just want to stop execution, but you still maybe want to start it later. You still want to keep everything set up. You have the suspend and resume. They don't return anything, they return void. So all you have to do is just provide that thread ID. And we saw that earlier. This kthread create actually returns the thread ID. So that's kind of important to keep in mind, or keep that somewhere, especially if you want to suspend or resume execution. So one thing I mentioned earlier was the thread termination. And that happens when you just return from that thread function, or they call it the entry function. In this case, it's our UR_thread. And you can also use the k_thread abort function, but that's kind of like a sledgehammer. Like it'll just like totally stop it in its tracks, and it doesn't kind of gracefully deallocate anything. So generally, don't use that if you're writing any type of code that's using it, unless it's like kind of a destructive thing where it's like you're trying to just, stop a thread completely right before you're going to reboot the device or something. That might be an option for using that type of function. But generally, use the start, these two functions, the suspend and resume. And then another thing that popped in my head as I was doing this presentation was like, okay, you have these threads. Like they're processing something, but it's kind of tricky when you are creating these threads, because sharing data between these threads, you can't just like create some type of static variable that's shared between two threads, because it could change and it could cause any type of memory issues. You're not getting the right value passed across to the other functions. So my favorite way of handling it is using message queues. And what I do is I create a common struct. So this struct might have different types of data types. I actually use an embedded union of different structs, so I can share that data across. Maybe you're passing different types of data depending on the situation. So I'll show you that in a second. And we're defining that message queue to use that struct, that common struct, and then we're using the put in get methods to get that data across. So I'll show that in a second. So this is an example of having an event type. So that tracks whether or not it's a GPS, an AGPS request, a motion data, or an error. And then you see that union there of all the other data pieces of data. So whenever it's a GPS data, we're going to be referencing the GPS_data variable within that struct. It's kind of a way to create this blob of bytes, and it allocates the maximum amount of bytes. So whatever's the biggest struct within that union is going to define the size of that app event struct. And that is what we use to actually define the message queue. So the message queue size actually defines how many entries or of that struct that we're using, and then we can use the size of method to actually get the size of the struct itself. And what we're going to do here is we're just using this outgoing message queue, and we're going to be putting data on and pulling it off. So you can see here with the K message queue put, we're just putting on some type of event that was created earlier. And maybe this is in one thread that's creating, so we maybe in the UART thread, we're creating this message and it's going to get pushed to the main thread. And then in the main thread, we're kind of waiting. Either we can kind of lock the thread where we can wait forever, or in this case, this is a example of not waiting at all. And we're just getting, if there's a message that's available, we're just getting it, and then we're pushing it to some other event manager or pushing it to the cloud or whatever. So it's the same way of keeping memory, your data passing from one place to another between these threads. It's one of my favorite ways to do it. But if you have any other ideas or ways that you like to pass information, data between threads, feel free to let us know in the comments, because the more information we have about this, I know there's some other like shared memory constructs. There's some FIFO. You can actually dynamically allocate things on the heap, and then you just have a queue of pointers. That's also another way to do it. I'd like to avoid allocating on the heap as much as possible, so I don't break my application in the middle. Because as much as you test things, there's always something that breaks. So. And quick summary. So they're great for controlling disparate functionality in your code. So you have a main function, you might have a UART processing function. I know for me, I have like a cloud client, and that has its own thread for processing events as they happen, and also sending of data to the cloud, or encoding, decoding. And they can be created, stopped, started, and terminated within a runtime context. So like one thing that one of my customers has requested is like, I just want to turn off the application logic. I want it to still run, want it to still be connected, but I don't want the application to run with a remote command. So that's something where it's like, okay, I can just turn off that thread if they don't need it. So it's an option for you if you need to turn off the thread for whatever XYZ reason. Just remember that you have to, I'm going to beat this dead horse, but allocate that stack beforehand, because otherwise you won't be able to create a thread. And just be extra mindful about how you share data between your threads. This is probably the biggest gotcha in any type of RTOS where you have multiple threads. Shared data context is like, I've shot myself in the foot a lot where I'm not properly sharing data across threads, and it's just like, why isn't this working? Why is this locking up? Sometimes it's like you're allocating memory on the heap, or you're using an amount of stack space that's not getting released. Or sometimes it's like something like this, where it's like you're just getting bogus data from another thread. It's like, what is going on? It's like probably not shared properly. So bear that in mind. And that's it for today. This was a quick one. Let's see, 19 minutes. If you haven't already, jump over to jaredwolf.com and subscribe to my mailing list. I actually sent out an email before this about 30 minutes ago, 50 minutes ago, just letting you know that this video is coming down the pike. So please do subscribe. And of course, I don't spam. I don't do anything nefarious. Just there to share more information that may not be able to share here on YouTube. So, and yeah, really appreciate you being here. I'm going to see if there are any questions. Hey, yeah, Gaia. Yeah, you're very welcome. I know this is a topic that is near and dear to many people's hearts. Cool. I don't see any more questions, but I'll hang out for another second or two. And of course, I don't want to cut myself off. So, but yeah, appreciate it. All right, that's it for now. And really appreciate you being here today. And we'll see you on next week. If you have any topics that you'd like to discuss, or you'd like to see me discuss, or we could, of course, discuss it together, you can leave a comment down below, shoot me an email, jump on the community forum, which is all in the description below, and send me a message, and maybe I'll cover it in the next Zephyr 101 live session. So until next time, see ya.